So yeah, I guess we worked on this paper before ChatGPT came out. So for a bit of context, I unfortunately couldn't rely on OpenAI's tools to write this paper for me. This all had to come from our collective intelligence. But I'm going to go over a bit of an overview of really what the paper is, what it's motivating, and perhaps what's wrong with it, and where it's going, right? So we'll start off with why spikes, right? Why do we want to make our neural networks all spiky? And it really comes down to this. The fundamental unit of computation in the brain is a spike, right? And we like the brain because the brain is pretty damn power efficient, especially when you compare it against the ridiculous amount of GPUs in server-based environments that, I guess, modern language processing requires. And it makes sense to use the brain as a bit of a blueprint on optimizing AI. So a long time ago, evolution determined that the constraints of the brain meant that spikes were effectively the most optimal way to encode information, and we're really going to explore when and how this logic can apply. And I mean, to be honest, all spikes very much look the same, right? They've got an identical pulse width, their amplitude is identical. So how do we distinguish them, right? And it's kind of thought that we really just care about the timing between spikes or the order of spikes between neurons or how long various neurons might take to spike between them, this inter-spike interval, right? What all of these have in common is the notion of time, right? So while AI relies on the amplitude of activations, it's thought that spiking neural nets have a little bit more richness to them. So the working theory is that the brain compresses the entire environment into something that looks like spike timing. So how can we take advantage of this? Let's dig into this idea a little bit deeper. And of course, if I was to model the biological neuron perfectly, then it would be a ridiculously complex series of equations. It would not be perfect because it's just so rich in its dynamics. So quite a long time ago, we're talking on the order of a century of time ago, we introduced the leaky integrate and fire neuron to abstract a lot of the complexities of biological neuronal dynamics. And just to give you a bit of qualitative intuition on what the leaky integrate and fire neuron is, it's something like this, right? You've got this node, and over time you might stimulate it using a set of input currents. And if that neuron is sufficiently excited, then it will trigger its own spike to all of its downstream connected neurons. And I guess what's nice about that is if the neuron isn't spiking, then it isn't communicating anything, right? And communication, data movement really is the primary cause of inefficiency in pretty much all deep learning workloads, right? So in absence of spiking, in theory, in principle, with the right hardware, you're able to get around any sort of downstream processing. And so that's nice. So what's going on here, right? Let's treat the x-axis as something that moves forward in time, and we're applying some input current stimulus to this neuron in response to the first spike current. Then the membrane potential, that is, the voltage between the intracellular and extracellular medium, the inside and outside of this neuron body, it jumps up in response to that first spike. And then we remove the spike, like you've kind of clipped it, right? But that membrane potential doesn't immediately disappear. It kind of lingers for a bit. It exponentially relaxes back to its steady state value. So it's got this sort of short-term memory property. And then if I was to apply a train of spikes, as happens a little bit later in the simulation, then that rise starts to kind of accumulate on top of itself. It integrates, right? And so we've got the leakage, right? That is the membrane potential relaxing. We've got the integrate. That is the membrane potential kind of riding up on top of itself. And then finally, in order for this neuron to fire, it has to reach a threshold. And so I've kind of arbitrarily set this threshold of 1. And that is what happens. So that black dot here is effectively modeling this idea of a binarized spike being transmitted to all of its downstream neurons. So with that being said, that's just a very high-level qualitative overview of what the leaky integrate and fire neuron is. And the idea is, can we replace all of the nodes in an artificial neural network with this slightly more biologically motivated model, with the goal not of emulating the brain exactly, because there's just a ridiculous amount of work to do in that space, but rather to extract a bit more efficiency without a degradation in your deep learning model performance. And of course, there's a little bit of more quantitative math here, where you can express this biological neuron using a continuous time ODE, a dynamical equation. Now, if you were to solve it, and there is such a solution in a closed form, then you'll be able to find the membrane potential at the subsequent time step is going to be the previous membrane potential scaled by some factor beta that lies between 0 and 1. So for example, if the factor beta was 0.5, that's effectively me saying that the membrane potential is going to get halved at every time step. And that is exponential decay, right? 1 goes to 0.5 to 0.25 to 0.125 and so on and so forth. And meanwhile, we're also adding this new current input, right? So what can we do with all of that? We can express that in a recurrent format if you have a discrete time solution. So for example, our current injection is now just the product of x and w. X is our input and w is a learned weight parameter. We generate a membrane potential and you check if that exceeds your threshold. If so, then you generate a spike. If not, then don't transmit a spike. And that membrane potential is going to be scaled by that linear factor beta. And you just kind of keep doing this again and again. Meanwhile, you're checking if the membrane potential exceeds a threshold and so on and so forth. And so the spiking dynamics here can be represented by a step function. H stands for Heaviside here, just a cute little step function where if you exceed the threshold of the step, you generate a spike. And if you're below the threshold, then there is no spike. If we want to be a little bit more explicit about this, then we can unroll this recurrent computational graph where every kind of column, if you will, represents a single time step of the simulation. So again, the membrane potential is just getting scaled by beta time and time again, and that's all well and good. Conveniently, neural networks are also this sort of acyclic computational graph where, in this case, the current input is just x that varies over time multiplied by some weight w, where in this picture it doesn't vary over time, but there's nothing stopping you from changing that assumption. And because we now have this acyclic computational graph that represents this leaky integrate and fire neuron, we effectively have a model that is now compatible with all of the tricks and all of the hacks that go with training deep learning models. So if you see an advance in deep learning, then fingers crossed you're able to port them over to a leaky integrate and fire neuron or a network of leaky integrate and fire neurons. We have a spiking neuron. How do we scale this up? How do we make it functional and useful? So let's consider the various ways that we can train a spiking neural network. I'm going to go through a bunch of these that are kind of expressed in the paper. We've got local learning, which we're going to start with, and we've got a series of other techniques that vary in how much inspiration they take from deep learning. So what is local learning? Well, rather than explaining what local learning is, let me give you an example of local learning. And one possible learning rule that we know is biologically plausible is spike time dependent plasticity, or STDP. And honestly, it's quite straightforward, right? You have a pair of neurons that are connected to one another. You have a presynaptic and a postsynaptic neuron, and if this presynaptic neuron spikes first, followed by a spike in the postsynaptic neuron, then it's expected that the weight between these two neurons should increase. But if you flip that order, then that weight should decrease. So it's kind of thought of as a bit of a causal relationship, right? This presynaptic neuron is causing the postsynaptic neuron to fire, and therefore we should reward that causality. And back in '98, this, I guess, plot of the timing difference between the two spikes was kind of experimentally shown to follow an exponential relationship with respect to the change in conductance, right? So you see a positive weight update given a particular sequence of spikes and a negative or reduced weight update given the opposite sequence of spikes. So connections are strengthened if the neurons fire together and they follow a certain causal sequence. And if I can just really abstract this away and simplify things down into bite-sized pieces, the pros of this of STDP is that it's biologically motivated, right? Like it's literally derived from experiments, right? And it's computationally cheap. And hopefully you can appreciate that because every single weight update is a function of the nodes that are immediately adjacent to the weight, right? If you think about gradient descent, backpropagation, and all the fancy deep learning hacks, well, you're relying on a rather complex computational graph that has to be mirrored in order to execute gradient descent with some global loss function. And so there is an insane amount of data movement in backprop, right? Whereas here, we're updating this weight based on purely local signals, so hence this local learning rule. What are some of the drawbacks? It's not very functional in the deep learning context, right? And why should it be, right? It's not an optimization algorithm, right? What's kind of fascinating is that since about 2014, 2015, people did take this STDP learning rule and they did try and solve functional data-driven tasks. Think like the MNIST, fashion MNIST dataset. And they were able to use this kind of unsupervised mode of learning in order to achieve accuracies that exceeded 95% on these datasets. That in of itself is kind of mind-blowing, right? Because this is not functional optimization. This is something ripped directly from biology, right? There is no reason why it should work, and yet it doesn't do too badly, right? So I kind of want to move away from this idea of comparing backprop with STDP rather than they're just kind of serving two very different purposes. So we've got STDP. Let's briefly consider shadow training as well. And it's quite simple. The idea is that we take an artificial neural network and you use some, you pre-train that using gradient descent, using vanilla deep learning tricks, and then you convert that artificial neural network into your spiking recurrent neural network. And some of the pros here is that it was kind of the first approach to really reach state-of-the-art performance or compelling performance on more complex tasks, right? So we're talking your ImageNet, Cypher10, those types of data sets. And if you consider it a pro, then you also end up with a pair of networks. One could be argued for performance, and one could be argued for power. And there was a cool paper a couple of years ago at ISSCC from Georgia Tech, where they indeed had an artificial neural network and a spiking neural network, one on SRAM, one on RRAM, kind of stacked on top of one another. And every time they needed something high speed, they switched over to the SNN. And every time they I guess, needed just something robust, something reliable, something a little bit more deterministic, then they shifted over to the ANN. But some cons are that the SNN is effectively an approximation of the ANN, right? You're converting one to the other, and therefore this guy, your artificial neural net, sets an upper bound on performance of your spiking neural net. You're never going to surpass performance here, unless you run into some happy accidental regularization, which is probably not going to happen. Not at least for complex tasks. Secondly, one of the drawbacks here is that sequential ANN conversions, so your LSTMs, your artificial neural nets, etc., it's a very underexplored area. This mode of training is really only being tested on image-based data sets nowadays. And it also scales, it doesn't scale crazily effectively, right? And finally, it seems somewhat biologically implausible in the sense that my brain is probably not training some artificial clone of itself. So if you care about that, then this might not be the way to go. But I still have to respect it, right? Because it got people looking at how to use deep learning in the context of spiking neural nets. Let's briefly consider spike time learning, and I think it's really worth looking at because it really was the first technique to do optimization on a spiking neuron back in 2002 by Sundar Bote. And the idea is this: you take the derivative of the membrane potential with respect to time only at the firing time, and then you can use regression, right? Now, of course, spikes are thought to be non-differentiable, right? You've got a Heaviside step function, and we'll visualize that in a moment. But if you're taking the derivative of this continuous and mostly smooth membrane potential, well, yeah, of course I can take du on dt at a particular spike time, right? And I can optimize this firing time to fire earlier or fire later, right? And that's a regression problem, right? So some of the pros, well, it was the first use of backprop on spiking neural nets. And that kind of gets me excited, right? Got to respect the history. And it also leads to very sparse spiking activity because you're effectively rewarding one spike at a time. And now we've got this long list of cons and drawbacks. So potentially you end up with a model that is arguably too sparse. If I'm trying to do something that looks like deep learning, then one spike is a difficult thing to work with. Learning one spike at a time is challenging you. You run the risk of having to execute a chunky for loop for every single spike that you want to elicit. Secondly, if there is no spike, then there is no learning. There is no well-defined gradient. It also forces you to use spiking neuron models that have differentiable voltage dynamics. So the leaky integrate and fine neuron that I showed you a few slides ago, that is effectively quite differentiable at the spike time, right? You have this sudden jump of membrane potential that exponentially decays. So that decay is fine, that's smooth, but that sudden jump is not smooth, right? And so you would have something non-differentiable at this point here. Of course, there are ways around it. One way around it is using a second order spiking neuron model that accounts for synaptic current, which is what I've got shown here. It hasn't performed too well on challenging data sets yet either, and it is very sensitive to hyperparameters. And so over the past 2 decades, this approach has been extended to handle alternative cases, multiple spikes, alternative neuron models. A bunch of extra hacks have come about where if you don't have spiking, then you just introduce a ghost spike at the final time step. Event prop by Christian Pele is one example of an extension or generalization of this spike time learning. What seems to have really exploded was backprop through time and surrogate gradients, right? And so that's what we're going to kind of focus a little bit more on. And the idea is this: you've got your neural network, you've got your spiking neural network, which just so happens to be an acyclic computational graph. And before I explain what it is and how it works, let's look at the pros and cons. It is no longer necessarily upper bound by the limit of ANN performance, so we can effectively reach state of the art on most tasks when compared to alternative SNN learning rules. And of course, PyTorch and TensorFlow really changed the landscape of the accessibility of deep learning. If we're doing backprop and ANN tricks on SNNs, then you've got something that is perfectly compatible with those very same tools. So, if you come up with a better optimizer on recurrent models, then bam, you can steal that and make your SNN a little bit better. Cons, of course, there's some drawbacks with all of the benefits. It is computationally expensive. I've listed here on non-neuromorphic hardware, but you could ignore that, right? It's computationally expensive, full stop. It is still somewhat sensitive to hyperparameters, especially when you compare these models to their non-spiking counterparts. And it's also pretty biologically implausible. Depending on who you talk to, Conrad Cording might tell you that, hey, gradient descent is probably approximated in the brain, so maybe he's got a different opinion, and I think that's all well and good. It's pretty interesting to think about. You introduce this temporal and spatial credit assignment problem in the sense that how likely is it that the brain has a perfect memory of the forward pass when training every single weight, right? Not very likely. The brain is more like this active learning machine that is updating during that forward pass as well. So how can we kind of bridge that gap? So let's see. We've seen this before. We've seen this computational graph before. And the way that error backpropagation works is that you generate some loss at the output and you apply the chain rule, just a iterative application of these derivatives of every single one of these nodes, propagating back to all of the weights that, I guess, generated the final loss function. But this is just a one-time step, of course. We need to propagate this error back one more step and another step and another step. And keep in mind, this is just for one single neuron simulated over 1, 2, 3, 4 time steps. So we're really talking about doing this at a very large scale, right? Which can be pretty damn expensive. And of course, we've got the non-differentiability of spikes, which I think is kind of common knowledge now as to its solution, where if I want to generate a spike, well, my membrane potential needs to exceed this threshold. If it exceeds the threshold, then beautiful, I get a spike. And if not, then I do not get a spike. I get a 0 or a 1 kind of behavior. But if I take the derivative of this step function, then I get this Dirac delta. And so this term, which is pretty much 0 across almost its entire domain, if not 0, then infinitely large, that is effectively going to swamp out every single derivative term across this entire computational graph, right? How do we fix that? Well, Emre has a wonderful paper out that kind of examines the surrogate gradient in a lot more detail. And the idea is really straightforward, right? On the forward pass, you stick with the step function, but on the backward pass, you take the derivative of a smoothed out approximation. And in doing so, it works surprisingly well. I don't know if it's all that surprising either, because at the end of the day, when you're training deep learning models, we use optimizers anyway, right? You have stochastic gradient descent with momentum, you have Adam W, and so on and so forth. Every year, there's another 100 of optimizers that are introduced. And so what that is to say is that we're not using the exact gradient anyway. And this just shows that particular types of perturbations, particular approximations of the gradient are still going to end up helping you or being tolerable. And that's exactly what's being observed here. And so what this paper kind of released was this Python library, SNNTorch, that I spent, I guess, 2-3 years in Professor Weilu's lab at the University of Michigan during the COVID era, developing. It's open sourced on GitHub, and it effectively makes all of these ideas of training SNNs with deep learning hacks just a lot more straightforward. So if you know PyTorch, it's very easy to pick up SNNTorch. It's kind of exploded a little bit, exceeded 200,000 downloads, and more recently with the advent of intermediate representations for neuromorphic software, led by Jens Petersen, it is now also compatible with all of the neuromorphic hardware tools that are out there, from SynSense to Intel. And a couple of other cool places are using it in practice too. NASA, for example, are exploring how to do satellite tracking with spiking neural nets. You know, if you point a telescope into the night sky, what is there? Just a lot of nothing. So if there's a lot of nothing, then you may as well not process the entire image, right? And so spiking neural nets seem to be really well tailored for those types of sparse workloads. It's also a really good way to kind of get into the field of SNN. So if you're listening in and you're not super familiar with the low-level details and you're like, damn, that's going too fast, break it down for me, man. These tutorials do that for you. So I would strongly recommend you take a look. You can just Google SNNTorch tutorials, and all of this code is very interactive. It's yeah, quite fun to go through. And so with all that being said, I'd really like to take a brief moment to highlight the link between STDP and backprop. We often, in the neuromorphic brain-inspired machine learning community, we keep hearing these stories of how backprop works way better than STDP. Oh, but STDP is way more biologically plausible than backprop. Do we really need to be putting them into this cage match fight against one another? Not necessarily. If you really think about backprop, right, as you're traversing back through your computational graph, and when I say back, I mean back in time, right, from right to left. What you're actually going to end up what you're actually doing is taking some derivative, partial derivative that you're calculating, and you're scaling it by beta, right? And that is because the derivative of this node with respect to this node is beta. And so the further back I go in time, the more times I'm going to scale it by beta. Now recall, beta is some value between 0 and 1. If I multiply a number by something between 0 and 1, it's necessarily going to shrink. And if I keep doing that again and again, over time, as I go back in time, I'm going to get some sort of exponential decay, right? So what that is to say is that STDP and backprop through time specifically, when constrained by this beta parameter, they actually look surprisingly similar to one another. And one thing that is mentioned in this Proceedings of IEEE paper is that, hey, why are they fighting? Like, couldn't they get along a little bit better? Couldn't STDP potentially propose some sort of efficient local learning mechanism that just with backprop just subsuming this temporally varying credit assignment issue, right? And so I think that there's a lot to explore in the interplay between the functionality of backprop and the, I guess, biological plausibility of spike time dependent plasticity. And I think this link is really quite profound because the two of these two ideas came from completely different means, right? Backprop it's calculus, right? It's literally functional optimization. STDP is a couple of dudes that are sticking probes into neurons, right? It's an experimental, it's a model of an experimental observation, and yet they have this kind of beautiful link, right? So yeah, there's a lot to be said. There's a lot to explore here. Now, on the final notes of the how to train your spiking neural nets, let's consider real-time recurrent learning. This will be kind of abstract, a little bit high level. And the idea is this, there is a bit of a problem with backpropagation through time. And that is, if I'm going to propagate errors back in time from right to left, that implies that I need to store the values of every single node during my forward pass. I need a perfect memory of everything that I have ever done. I mean, do our brains do that? Probably not. I think my brain would melt, heat up, and explode if it tried to cache every single state that it's ever been in. I mean, my brain already doesn't work very well, but this would just cause it to fry. As a result of this, the backprop through time algorithm has a memory complexity of n times t, where n is the number of neurons and t is the number of time steps of simulation. And you can see that one extra time step is going to add an extra set of computations that need to be backpropped. This kind of idea of real-time recurrent learning or forward mode learning addresses this, right? Where gradients are snowballed forward in time. What I think is interesting is that it was actually proposed back in 1989 by Williams and Zipser. And it goes something like this, right? Let's say that I've only processed my first time step of simulation, right? I've gone up, I've generated a loss at t equals 0. I haven't yet gotten to t equals 1, 2, 3 yet. But the moment I get here, I am able to run a backprop pass, not through time, but through space, right? Through layers. That's all well and good. Now let's say that I step forward one time step to t equals 1. What can I do? Well, I can take some partial derivative that might have come from these particular nodes. I can push that forward through this beta term, right? Remember, during backprop through time, we had to go back through beta anyway. Now I'm saying instead of going back through beta, why don't we just take this guy, push it forward through beta, scale it by beta, and then, which in this case is just x0. So it's like taking your input and pushing your input forward through time. You might have heard of eligibility traces, and that's kind of what this is getting at. And now I have all of the spatial information that I need here, and you just kind of repeat this. So not only are you, I guess, snowballing your state forward in time, but now you're adding a couple of extra variables and you're snowballing your gradients forward in time. And by the end of it, you've effectively re-implemented the backpropagation through time algorithm just using a different sequence of steps. So they can be functionally equivalent. They don't have to be, and the case where they don't have to be is where you regularly update your weights through time, whereas the backprop through time doesn't have a weight update until the end of your simulation. So what if this is all well and good, like we're seeing a case where I no longer need to store my membrane potential because all of the gradient information that I need is moving forward at the same time as my forward pass. So, this is great. You've solved the temporal credit assignment problem. I don't need to store multiple copies of every single state that my brain has experienced. Why isn't it the de facto training method in modern deep learning? Well, it was buried and somewhat forgotten because RTRL, real-time recurrent learning, comes at a cost of n cubed. You've sacrificed time, you've gotten rid of time, but now we have something with cubic complexity, right? And this makes a lot less sense when we end up with neural networks that have, 5 trillion parameters in them with a lot less time steps, right? So RTRL didn't ever quite lift off, but more recently, we are starting to see spiking neural nets applied in the context of RTRL. And Emre's group just released a preprint last month. And I think that he can speak more to this during the panel discussion, but he's effectively identified that there are key differences between recurrent neural nets and spiking neural nets, right? And some of those key differences reduce that n-cubed complexity to something far smaller without necessarily degrading performance, right? And I'll go through what some of those key differences are in a moment. So SNNs can very well accidentally fix this, right? If I want to highlight exactly why they accidentally fix this, let's now be a little bit more formal, right? Let's consider one layer of spiking neurons. We have 3 inputs, and each input is being passed into a spiking neuron where the beta decay factor is now represented with W. If I wanted to formulate this in terms of some sort of vectorized expression, then each of these values of V represents the membrane potential or the hidden state of each of these 1, 2, 3 neurons, right? And this state is going to be calculated on the basis of a diagonal transition matrix multiplied by the state at the previous step, added to the current time input. So V1 is going to be this recurrent connection multiplied by the previous step V1, denoted by this subscript, plus 0 times V2 plus 0 times V3. So really it's just V1 that's influencing itself, right? So in a way, the hidden state is perfectly local. There is no influence from these two guys on this guy. And the same thing applies to V2 and V3, right? So I could re-express this diagonal matrix into this Hadamard product form, right? I could just say W1 times V1, W2 times V2, W3 times V3. And that's all well and good. If I want to iterate over time, then t equals 2, we'll just update the subscripts and so on and so forth. I want to make a key distinction between spiking neural nets and recurrent neural nets, because this often goes missed, right? With recurrent neural nets, it's more like an all-to-all hidden state update, where all of the hidden states are passed through a dense layer, followed by a nonlinearity, which then gets passed back into these neurons. So the way that that's mathematically expressed is effectively by a dense transition matrix. It's no longer diagonal, right? So in other words, W1, I guess superscript 1, 2, 3 are all going to influence V1, right? So all of this information, all of these hidden states are kind of mixing in together. And not just that, but you've also got this nonlinearity applied to this term, right? So with that being said, let's kind of place these two things side to side. RNNs have this all-to-all recurrence and they're nonlinear through time, whereas SNNs have one-to-one recurrence and they're linear through time. Remember, we're talking about this in the context of real-time recurrent learning. And I'm trying to show you that SNNs are cheaper without any sort of loss of generality, right? So you can already gain some intuition in that this element-wise operation is already cheaper than this matrix vector multiplication, right? So that is one angle that contributes to the better complexity of SNNs. But of course, you will justifiably have this concern that, hey, well, if SNNs just have 3 parameters, right? In this 3 neuron case, you've got one state per neuron with only 3 parameters. Aren't I losing something? Isn't there like less capacity to learn or something? So let's explore that in a bit more detail, right? So really what I'm trying to say is, or ask is, are recurrent neural nets more expressive than SNNs as a result of this reduced computational complexity? So let's bring up this equation again in vectorized form, and let's now pull up the equation where I iterate through one time step, so the second time step of hidden state, and I'll substitute in V1, this WV0 plus X0, into this term, right? So all of this guy is just going in here. And you can probably see where this is going, right? If I expand out this bracket, then I end up with W squared. I end up with matrix-matrix multiplication. That follows n-cubed complexity, much like RTRL, which is not a coincidence. What about SNNs? So this linear SNN, ignoring the reset mechanism for now, if I do the exact same sequence of operations, I end up with W squared. And keep in mind, this is just t equals 2, right? If I iterate to t equals 3, then we get W cubed, W to the 4, right? We get matrix, matrix, matrix multiplication. Then element-wise products are just linear, right? If I add one extra element to this vector, then that's just, linearly increasing computation. And this is very cheap, right? So happy days. Of course, we sacrificed a whole heap of parameters in order to get here. So let me try and convince you that SNNs don't actually lose much as a result of this. Let's assume that we're back in the recurrent neural network case where a square matrix W, right, the transition matrix, is diagonalizable. So P could be a matrix of eigenvectors, D is your diagonal of eigenvalues, and we've got P inverse. Now, if I bring back our hidden state equations, W squared is really what we care about, right? So W squared is just going to be PdP inverse times itself. And if you pay close attention to this guy, we can play a little trick. P inverse times P is the identity, and we just end up with D squared, right? And so a diagonal matrix multiplied by itself is just, it can be casted as element-wise, as an element-wise product. We know that element-wise products scale linearly with extra elements. And so what that is to say is that with spiking neural nets, if I was to just take the element-wise operator, that is beta, the decay rate, the transition vector, and as long as I have some value of P and some other value P inverse, which are not changing over time, right? And these values not changing over time kind of imply that they might just be linear layers, right? They could be linear layers that don't need to be backpropped through time, right? Then I'm onto something, right? Then I'm able to do something recurrent that is only scaling linearly. Now, the inverse of matrices is always challenging to compute. In the deep learning literature, what they tend to do is just sub out P inverse for some learnable matrix Q. Therefore, this term is no longer perfectly equal to W squared, but ultimately the point is that we're just trying to show that this has the same sort of capacity, representational capacity, as the alternative. So yeah, in practice, what's really done is your P matrix is just a learnable nonlinear linear layer, a channel mixer. And then we apply recurrence through the spikes. Then we concatenate that with another linear layer, which is what we already do in the spiking neurons, right? And so as a result of that, you can apply real-time recurrent learning to SNNs, and provided that you have these, I guess, linear layers, dense layers with nonlinearities abutted to them, then you get the same sort of expressive power as a recurrent neural network. With all that being said, where are we headed to? What's the future of spiking neural nets, and what application domains are they kind of in right now? So my group has been working a little bit on a couple of cool tasks, autonomous driving and language modeling. I'll fly through both of them. In terms of autonomous driving, we recently released a NeurIPS paper where we kind of chained together three components: a perception model, a prediction model, and a planning model. The perception model is just trying to generate bird's eye views. Prediction model is trying to predict what's happening at the next time step, and your planning model is trying to say, hey man, should you steer to the left, the right? How hard should you hit your accelerator? But these three sub-networks are all end-to-end differentiable, where we train them sequentially one by one. And so this is nice because at the time of releasing this SNN paper, it was really the case that spiking neural nets were only being kind of benchmarked on rather toy problems, right? So we're really hoping to try and push that out. And initiatives like the Neurobench framework or the Neurobench, I don't know what to call it, benchmark, are really trying to push that out, right? You're trying to do more functional systems level tasks, which I think is really cool. Language modeling is probably what my group's really invested in a fair bit more detail. So with language modeling, if you think about self-attention, we take this sentence: Sundar saw Mark with binoculars, right? Sundar saw Mark with binoculars. Now my question to you is, who has the binoculars, right? Is it Sundar or is it Mark? Linguistically speaking, this is ambiguous, right? I don't know who has the binoculars, right? It could be Sundar, it could be Mark. But with a bit of context, with the knowledge that our Google tech overlord saw somebody else, it's probably Sundar that has the binoculars, right? And so in modern language modeling, we'll take Sundar as a vector, as an embedding. Every word, well, technically every token is represented by a vector. They go through a series of linear layers, a bunch of operations are applied to them, and ultimately you end up with what's known as a self-attention matrix, which is just trying to figure out the relationships between every word and every other word. So in this example, what you're really seeing is a perfect memory, right? If I added an extra word, I'd get an extra vector, and this vector has access to the first vector, right? In this example, I'm going to show you Sundar and binoculars both light up. And so there's a strong relationship between Sundar and binoculars. Mark and binoculars also light up because we've got, I guess, a subject and an object, but it hasn't lit up as strongly as Sundar because, again, self-attention with modern language models have perfect memory, right? Now, if I was to kind of take this and indefinitely add extra tokens, then you would see this matrix growing across both the x dimension and the y dimension. So your self-attention matrix, your memory, is going to grow quadratically with increasing sequence length. And I think it's very unlikely that our brains are undergoing neurogenesis with every additional word that I say. But then the issue with spiking neurons is that, by the time I've reached the final token, there's a very high chance that I've lost all information about Sundar, and Mark has kind of replaced that. And if you think about the spiking neuron, well, if you could think of this first spike, this first state jump, as representing Sundar, and by the time you've gotten to the end, it's all but faded away, right? And so in attention, you have too much information, and with spiking neural nets, there's not enough information. So we introduced Spike GPT with the hope of overcoming some of these challenges, and it was at the time the largest spiking neural net trained via backprop, the first to perform language generation, but really it was only possible because we didn't solely rely on leaky integrate and fine neurons. We relied on a large number of additional stateful operations. And I've got a set of, I guess, demonstrations of Spike GPT. If you saw this 3 years ago, you would be much, much more impressed. Now, ChatGPT is just kind of, I don't know, taking the front seat. But in either case, the fact that we got this done with spiking neural nets, I think, is quite a remarkable feat of itself. And you achieve this with 30x less operations than a conventional transformer. So of course, I like to always be self-critical. Why isn't the world using it then? And the honest to goodness answer is that scaling hurts. We try to take Spike GPT, which the largest iteration was a 216 million parameter model. We scaled it up to 1 billion parameters, and the performance improvement was so much more marginal than what a non-spiking neural network would have done, right? And that was a little bit disheartening to see. Does that mean that we kind of wasted all our time? I don't necessarily think so, because that effectively led us to this other line of work, the matrix multiply free LLM. And it's this first billion parameter scale language model that doesn't actually do any vector or matrix multiplication. You can probably get a sense of it. We actually used a mix of ternary parameters where -1 times some other value is just a bit flip, right, in 2's complement. So you can get rid of multiplication in vector matrix multi. But in addition to that, we're also using all of these element-wise operators, right? And SNNs taught us how element-wise products in the transition matrix is a really good way to retain the expressive capacity of recurrent neural networks. So we had ternary parameters. We also added this idea of learning how to forget, and we were able to generate some pretty good hardware metrics. I'm not going to go through this in detail, but we effectively brought back forget gates that came from the LSTM literature. If you want to go into more detail, then I recommend checking out the preprint. But the forget gate mechanism was effectively linearized. And in doing that, you're effectively able to remove information in order to make space for new information very selectively. So you go from this world where attention is too much information, but SNNs and more generally recurrent neural nets, when the Matmore-Free model is the more general case, now contain the correct information, right? Even though every neuron only has one state, as long as it's able to disperse of the useless information, it can make space for things that it actually cares about. Now, spiking neural nets and this Matmore-Free model are not built for GPUs, right? And so we had to kind of go ahead and build our own custom hardware solutions. On an FPGA, we were able to achieve 23.8 tokens per second at 13 watts, while human readable throughput is honestly a little bit worse than that. So happy days. We also have currently done a lot of work with Steve Abreu and Sumit at Intel on deploying the Matmore-Free language model on their neuromorphic processor, which was originally designed for spiking neural nets. And while Matmore-Free isn't a spiking neural net, it's retained a lot of the dynamics and benefits of SNNs, right? And if I show you some performance plots, this first one is very underwhelming, right? This Matmore-Free language model on the x-axis is the sequence length. So as we get higher and higher, then the Matmore-Free model in blue starts to do better than the Transformer++ baselines, where the plus models are all kind of the backbone of Mamba. Sorry, not Mamba, but Llama, all the open source model families. And on the y-axis, we have throughput, where higher is better. This isn't necessarily great. We were hoping for something a little bit nicer, right? But what this plot doesn't account for is energy, right? Throughput doesn't account for energy on its own. So when we do account for energy, then this is what we see, right? So joules per token on the x-axis, where higher is not ideal. We want lower. We want less joules for every token generated. And on the y-axis, we have throughput normalized for a single watt, right? And in that case, higher is better. I want more tokens per second given 1 watt of power. So these green circles are representing the Transformer++ baseline. This one is, I believe, the 2.7 billion parameter Transformer++ model. This is 1.3, so the diameter, I suppose, is representative of how many parameters. And in order to see where Matmore-Free lies on this plot, I have to zoom quite a long way out. And finally, we see the Matmore-Free model sitting over here. If I pause this video, the 2 iterations are doing far, far better. Less joules for greater throughput, for equivalent performance. But not just that, but remember, the Matmore-Free parameters are all ternarized, right? And so if I normalize not to the number of parameters, but to the amount of memory that they're using, where the Transformer++ baseline is in BrainFloat 16 numerical format, then we're able to get so much more for a lot less. And in terms of the language performance benchmarks out there, we effectively got the same results as Transformer++, or close enough to the same results. So with all of that being said, I want to leave you with a few lessons, and these are very opinionated, right? These are very personal, right? Lessons for spiking neural nets in 2025. So firstly, parallel training is critical. We need to be able to ditch the for loops. And in my opinion, linear recurrence is really the way forward. Now that is specifically for deep learning, right? If you're going down the road of brain modeling, then it's a whole different ballgame. But for deep learning, we need linear recurrence in order to reduce the computational complexity, in order to accelerate training. Secondly, A long-term memory hack is using data-dependent decay. That is, with spiking neural nets, we have that beta term that decays all of our values. You have that transition vector W1, W2, W3. But it turns out that if you make that matrix data dependent, if you make it a function of your input X, then you're able to get far better memory performance. Number 3, your next long-term memory hack, gating mechanisms. For get-gate specifically, if you have limited memory usage, as do RNNs and SNNs, then we need to be able to selectively forget information to make space for new information. Our brains do it very well. It makes perfect sense to do this for neural nets as well. 4, static sparsity is far easier to deal with than dynamic sparsity, which is a bit of a shame because spiking neural nets are dynamically sparse. The data flow that is dynamically moving, the activations, are sparse. But in my own personal experience, sparsity of weights seems to be far, far easier to train. Now, while it may seem like a bummer, I think it just kind of shows that there is a lot of untapped potential in figuring out how to make these types of models easier to train. And I think this might be my last point, but binary activations, are you sure about that? Right, so spikes are represented as ones and zeros, but we've seen hardware that is able to introduce graded spikes, which are integer-based spikes. And the idea is quite simple, right? If you're going to transmit a packet of information, then you may as well add a couple of extra bits or several or 8 bits in order to represent an amplitude and just compress a little bit more information in there, right? Computation is cheap. It's data communication that is expensive. And so keeping in some sort of multi-bit spike might really just be the way forward in terms of making computation easier and making spiking neural nets more scalable. Granted, that may not fit within your definition of a spike. I mean, firstly, I don't care too much, but secondly, it's also not going to impact your engineering capacity very much either. And we've got another one. So there are better ways to elicit sparse activation. Spiking neural nets are very naive in how they elicit sparsity. It's just a hard threshold, right? But we've now seen in production scale LLMs, mixture of experts. We've seen various ways to generate dynamic sparsity that work incredibly well, right? And so I think that what's really nice is that we are seeing a lot of things that SNNs were already doing pre-98, right? In terms of sparsity, in terms of element-wise local dynamics, things that a lot of modern LLMs, recurrent and otherwise, are now doing in 2025. So, there are a lot of lessons to be learned from deep learning in advancing spiking neural nets, but I think we are reaching this point where spiking neural nets have really taught us ways to potentially advance deep learning now. So, Dan, with that being said, I am happy to give the floor to Q&A and a 10-minute panel discussion. So yeah, thank you.